the previous one I showed how to set up the turbine with the charts and everything. In this one I'm not going to go through that again. I'm just going to show you what I did after that with adding the steam and gland steam on the turbines. Okay, in this presentation I'm just going to quickly go through the mass balance, the complete turbine train, and then how I modeled the HP turbine, the IP turbine and the LP turbine, how I designed the gland steam seals, the blade steam, and then connecting all the turbines together. For this presentation I highlighted the part that's applicable in the energy and mass balance here. As you can see there, the thick red lines are the main steam and the blade steam lines, and then the green, pink and orange are the gland steam lines. Just continue. Okay, this is the complete train of the Medupi center line. There's a single HP turbine with reheat to a double flow IP turbine and 2 double flow LP turbines. There's blade steam from the HP turbine exhaust, asymmetric IP and symmetric LP bleeds. And I've modeled each stage between the bleeds as a separate turbine because there's different steam flow rates going through each section of the turbine. So in total there's 17 turbines that I connected to one single shaft. This is just the mass flow through each turbine that I used to set up the turbine charts. This is taken from the Eaton mass flow calculations. So I'm not sure if you can see exactly there, but I worked out here the mass flow that's going to go through each section of the turbine, and I used these values to set up my turbine charts. Turbine charts will be in the next slide. So using the correct mass flow, it is possible to create a turbine chart for each turbine. Like I said in the previous presentation, I showed how I created the turbine charts, so I didn't include it here again.
So, yeah,
yes.
maybe I wasn't here, so I just wanted to know, is it a generic type of
yes.
chart?
It's a generic type. Rolf gave me an Excel spreadsheet that I could use to get it, so I just insert the values for a specific turbine, and then I get a chart that I can export and import into Flownex. Okay, this is a cross section of the HP turbine. As you can see there on the right hand side, number 7, the inlet scroll, and then by the balance piston there's some seals that's leakage on the HP side, and on each side of the turbine you can see there's 3 channels for the gland steam. The next slide will show you exactly how I just want to explain the pressure shaft seal. The shaft seals are provided with 3 outlet chambers in order to prevent steam leakage. The inner chamber is connected with the pressure relief system and discharges a big part of the leakage steam into the feed water. The middle chamber is maintained at a slight overpressure by the gland steam system, and the outer chamber is at slight vacuum. Steam together with penetrated air is discharged into the gland steam condenser. In my modeling of the glands, I didn't include the air that's going to come into the steam because I'm not sure if you can even do it in Flownex to combine the air and the steam.
You can.
Okay. I didn't include that. So
but it's probably very small. So you'd rather not do that in Flownex if it's not a major contributor. Otherwise, it's much more difficult to solve.
So this is the Flownex model of the HP turbine. As you can see there, in the middle, the small thing is the turbine, yes. And on the right hand side you will see the leakage over the balance piston and the 3 chambers there for the glands. Like I said, there should be another one with air leaking in from each side, but I didn't include that. Then the inner chamber where the excess steam will go into the feed water heating, the middle chamber providing pressurized steam, and the outer chamber that's going to be under vacuum. For the IP turbine, the gland seal is almost the same except for the innermost chamber. The intermediate pressure gland seals are provided with 2 outlet chambers, the inner to prevent steam leakage. In order to prevent steam leakage, sorry. The inner chamber is maintained at a slight overpressure by the gland steam system, and the outer chamber has a slight vacuum. The steam together with penetrated air is discharged into the gland steam condenser. I just included the overview there of the IP turbine. And you can see there the 2 steam bleeds in the middle of the turbine. That's also included there. So that's the reason why I had to split this one up in 4 separate turbines. And there you can see the 4 separate turbines with in the middle you can see from reheat, the steam coming in from the reheat, going through the first 2 turbines, and then down there's 2 orifices. Orify? I don't know what you where the HP steam bleeds are, and then going back to the second stage of the turbine, and then coming out to the next steam bleed, and then from there it will go to the crossovers over to the LP turbines with 2 labrum seals there for the inner and outer chamber of the gland seals. And then the same for the LP turbine again, the shaft seals is intended to seal up the exhaust area, but in this case it's under vacuum, so here you want to prevent air from going inside the turbine, where on the other turbines you prevented steam from going out into the turbine hole. The shaft seal casing is provided with 2 steam belts, one for connection to the gland steam system and the other exhaust system. The gland steam system operates with a slight overpressure and an exhaust system with a slight vacuum. The gland steam and the air drawn are fed into the gland steam condenser. And there's just a cross-section of the LP turbine. So here's the 2 LP turbines. You'll see because of the 4 bleeding points, I had to make more sections of this turbine. So for each turbine, I've got 6 sections of a separate turbine, and also the 2 chambers for the gland steam seals. Okay, to model the bleed steam, I had the set mass flow on a steady state for this model, so I wanted to size the orifice so that I can get that set mass flow from the turbine. Because this is an interconnected network, changing an orifice size on one of the bleed steam lines, it influences the upstream and the downstream mass flow. So when I get the first one, say HP6 and HP5 right, and I go to the deaerator tank, then when I get that one right, the HP6 and HP5 is wrong again. So first I tried to design it in the Flownex designer to design the orifice size to get the correct mass flow. I think there's like 12 interconnected variables that I need to design, and on my computer it didn't work at all. It crashed every time. So I'm not sure if it's possible to try it like that, but so to get it done a bit easier and faster, I used PID controllers to size the orifice to get the correct mass flow. And then I ran it with the steady state parameters in transient until it stabilized, and then I just deactivated the PID controllers to keep the size of the orifice. And that worked quite nicely. Then for the gland steam mass flow design, once again the gland steam mass flow is known for the steady state. I used labrum seals with the actual number of teeth and shaft diameters to model the labrum seals. And then I just used the Flownex designer to design the tooth clearance to get the correct mass flow. Then at the end of it all, I needed to connect all the 17 separate turbines together. So I just connected them all to one shaft, and I specified the shaft speed to be at 3000 RPM, and then Flownex calculated the excess power on the shaft that will go to the generator for generating power.
Yeah.
That's basically it. It's possible, in conclusion here, it's possible to model a very detailed system, and it's up to the modeler to decide how much detail he wants in the system. For me, it's a great visual representation of the flow paths of the steam of the turbine. Normally in the PNIDs, you don't get that detail of exactly where all the quantities of steam will go. And then in red, I just say that although the next release of Flownex will probably reduce all of this effort into a single component, for me, it was very helpful and a worthwhile exercise.